Hello everyone, welcome to this video. In this video, we will be solving this question which states that for every even integer n, we have to show that Dn, which is a group of symmetries of n-sided regular polygon, this group has a subgroup which is having order 4, right? So here you should know about dihedral group. It contains n rotations and n reflections, and we have several other properties for this, that when you compose a rotation with a reflection, you obtain a reflection. When you compose rotation with rotation, it is again a rotation. When you compose a reflection with a reflection, it is again a rotation. These three properties are there. Moreover, the inverse of any reflection, it is again the same reflection, right? These such properties are present for Dn, right? So therefore here, because we are taking n to be an even integer, in that case definitely we would divide 360 with n, so it would contain 180 for sure, right? So therefore we would have a rotation which is available for when we rotate it by 180 degree also for this Dn. It would surely be there because n is even, right? So it would contain R180, and if we assume f to be some reflection and h to be some subgroup such that it contains both R180 and f, in that case we have to prove that the order of h is 4, correct? So in this case, if we assume that within the subgroup H we have R0, which is the rotation by 0 degree, right? This is the identity of the group. We have the element R180 with us, and we have the element f with us. Then you see the inverse of all of these elements is present in H, because for H to be a subgroup we should have the two conditions, that first of all it should be closed under the given operation, and second of all the inverse of each element should also be present in H, right? These two conditions are required. So for these two conditions, we first of all check the inverse of R0, that is R0, which is already present in H. The inverse of R180 is also 180, which is R180, which is also present in H. Why? Because when you compose R180 with itself, you obtain R0. So therefore R0 inverse is R180. R180 inverse is R180, right? And for f, because any reflection composed with itself give you back the same figure. Why? Because when you perform the same reflection twice, you would get back to the original orientation as was there, right? So therefore the inverse of reflection is also its own, right? So f inverse is just f only. So here we notice that for H to be a subgroup, by the closure property, the inverses of all three elements are there. Now by the closure property, R0 composed with R180, it is just R180, which is already there. R0 with F, it is F, which is already there. But what about R180 with F? It should also be present in H, no? In order for it to be a subgroup. So if it for this to be present in H, we say we add this to H. So our H now becomes R0, R180, F and R180F, correct? Now let's check whether the inverse of this element is also present within H or not. If yes, then this forms a subgroup, otherwise not. So what is this R180F? Any rotation composed with a reflection. This is a rotation, this is a reflection. So this is another reflection, this property we know. And the inverse of any reflection is itself, so therefore its inverse, it would just be R180 into F. So it is already present in H. So we say the set H, which consists of these four members, this becomes a subgroup, because here the closure property as well as the inverse of each element is present within itself. Hence we found a subgroup of order 4 for Dn, where n is some positive even integer. So I hope you understood this question well. Well, that is it for this video. Thank you for watching.